Okay, in fact, I know that you are tired, but in science we have to suffer, you know that, so we will suffer a bit more, but we try to have a joint presentation with Stefan, so perhaps we will make it to be shorter. Surely he can do it, but I'm not sure I will be able to. I will try, in any case. So, in fact, we go at, in your diagram, Claude, we go at a larger scale, because I will consider only dislocations, and I will assume that in the material point you have enough dislocation moving and enough dislocation sources. So I am more at the micron, 10 micron and more scale, so speaking about crystal plasticity. But we will have one common ingredient, which will be the dislocation density tensor, and I will present a theory which I call the microcurl theory. This is derived from Ehringen's micromorphic model, and you will see how we will go towards crystal plasticity in this model. And in the second part, I will give an example of cyclic plasticity in a very simple case, and you will have the final answer to the questions given by Stefan. Okay, so the microcurl model is based on Ehringen and Mindlin's micromorphic theory, in which you have not only the possibility of translation for the material point, but you have also the possibility of an affine transformation of three directors that can rotate and that can also distort, in fact. And so this affine transformation is represented by a second order tensor. That's why you have a mustache like this here. It's a non-symmetric, because you have rotations and you have stretch. The P exponent here is simply to say that it will become something related to plasticity, which was not the case in Ehringen's theory, in fact. This is a first gradient theory. It means we include the degrees of freedom, but also their first gradient. So the first gradient is well known of the displacement here with respect to the Lagrange coordinates here. But in Ehringen's theory, you also introduce the gradient of the micro deformation. This is the quantity which was very important in this theory, but here I will not take the full gradient, which is the third order tensor. I will take only the curl. Why? Because I want to go into the direction of dislocation density tensor, and I don't need the full components of the gradient of chi here. I simply take the curl. So then this K tensor is a second order tensor, also without any special symmetry. You have to remember that in Ehringen's theory, the field of micro deformation here is generally not compatible. So it is not the gradient of a vector field, not necessarily. Can happen, we will see, but in general it is not the case, and this is the same for me here. Okay, so I want to present the theory at large strain, because simply to show that it's possible to have finite plasticity for micromorphic media, even though the example we will give, which are analytical, will be given in the linear case, in fact. So we start with a method of virtual power, and in the method of virtual power, based on Germain approach, here in fact, we propose a form for the power of internal forces, and the most simple one you can imagine, a linear form with respect to the gradient terms you have introduced previously in the kinematics. So we have the usual stress tensor here, which is conjugate to the velocity gradient. Here this is a small x, so the Eulerian quantities. But we have also stresses associated to the curl. So higher order stresses, I will call them double stresses here, and there is also a possibility of resistance for chi p. You will see later on why, in fact, this quantity can have a resistance S, which I will call the relative stress in the theory. And if you know that, you can compute the volume integral of a domain, and then you will see which kind of contact forces can be applied to the medium. And what you can apply traction forces as usual, but you can also apply double forces, surface density of double forces, small m, which react to the micro deformation that you have here. Okay, the balance equations are simplified Ehringen's balance equations. You have the usual in the absence of acceleration and body forces, the usual Cauchy equation with sigma being symmetric. But you have also Ehringen's second equation, but not the full divergence of a third order tensor, simply the curl here of these double stresses here. So we have two balance equations involving stress, three stress tensors. The boundary conditions are usual with the normal vector to the surface element here, where you apply the stresses, this one and the double stress tensor. Okay. We have to formulate some constitutive equations. We start from finite strain crystal plasticity, in which you split the deformation gradient into elastic and plastic part. Energy can be stored by means of the elastic strain. This is the green Lagrange strain, but with respect to the intermediate configuration in crystal plasticity. But now I introduce new state variables, and I propose this one here. Look at this E exponent P here. So you have the micro deformation, and you divide it by the plastic deformation, which is generally a non-symmetric, non-compatible slip tensor. And so it means you make the comparison between the micro deformation variable and the plastic deformation. And you take -1, meaning that if this quantity, if chi p is exactly equal to the plastic deformation, this quantity will be 0. So it means in this theory there is a price to pay for the micro deformation to be different from the plastic deformation. The state variables, elastic strain, this relative deformation EP here, the curl that we mentioned already. If you want, you can add your favorite internal variables for hardening, but coming from usual crystal plasticity. Okay, now you plug all these kinematics into the power of internal forces, and you split the elastic parts and the plastic parts. You have the usual one, the Piola-Kirchhoff stress with respect to the intermediate configuration, the Mendel stress, which is the driving force for plastic flow, and now we have new contribution. We have the contribution of double stresses here, and we have the rate of this relative strain with the conjugate quantity, which is the relative stress. You see that there is no special plastic contribution related to K. This is an assumption I state here in this simple model, that you store energy with K, with the curl, and there is no split into elastic and plastic. You can do it, maybe necessary in some cases, but in my example here, I don't need that. So really, the full K here, the curl of chi p, is used to store energy completely. Okay, though I don't go into the detail because it's standard anisotropic finite crystal plasticity. You plug it into the closed-use inequality, and you can postulate some hyperelastic constitutive equation. The usual one, the Piola-Kirchhoff stress on the intermediate configuration, so hyperelasticity is a standard one, and I postulate also hyperelastic relationships with respect to the curl, the dislocation density tensor, and here the double stresses. We have also a hyperelastic relationship between the relative strain here and the relative stress. Okay, the residual dissipation is due to plastic slip here. We have the plastic slip rate, we have the usual driving force here, and you have a new term. The coupling comes into play here based on this relative stress. Now you can postulate the flow rules as usual with plasticity. I will give an example. The example is to generalize Schmidt's law for plasticity. So you take a slip system with a slip plane with normal ns here, and the slip direction L, and you define the orientation tensor here. You project this curl S, that we have introduced here. This is this generalized stress, a combination of two stresses, and you project them on the orientation tensor to have a generalized resolved shear stress. There are two contributions in this resolved shear stress. You have the usual one, of crystal plasticity, simply the projection of stress on the slip system, and you have a new contribution coming from the relative stress here, and which I will call a back stress because it has exactly the form of internal stress in the theory. You have the positive part here, you have tau s minus x, so x can be interpreted as a kinematic hardening variable or back stress, which arises from the theory and is related to S, but as you remember from the balance equation, S is related to the curl of the double stress. So you have the curl of the double stress entering the kinematic hardening. Okay, let's consider a special case where you introduce an internal constraint. You enforce the condition that the relative strain is zero. So what does it mean? It means that the micro deformation is nothing but the plastic deformation itself. Now there is no distance between them, they coincide. If you do that, the K variable, which was the curl of the micro deformation, is simply the curl of the plastic deformation itself, and this is exactly the dislocation density tensor that Claude has introduced, and Kroner, it is the same definition as Kroner's dislocation density tensor. Okay, so the strain gradient plasticity that are based on the dislocation density tensor arise as special case of the micromorphic model you have here. Okay, so in the example we will do some linearized formulation. So simply the gradient of the displacement H here is split into elastic and plastic part, which are not symmetric. The elastic part is split into elastic strain and elastic rotation. Plastic deformation is split into plastic strain and plastic rotation. In fact, you can linearize the expression of the relative strain here, relative deformation here, and you see that this is simply the difference between the micro deformation here and HP, the plastic part of the gradient of the displacement here. I drop the hat here because I remove -1, going from the finite strain to the small strain assumption. So the equations are much more simple. Hyperelasticity for all stresses here, a plastic flow in the usual sense, but with this generalized stress here. And we will give an example. In mechanics, when you try a new model, of course, you start with something simple, so you take a quadratic potential for the energy. So I take Hooke's law here, and I consider two contributions which are quadratic in the relative deformation and in the dislocation density tensor K here. I introduced two parameters. I could introduce more, but for this example here, I take simply one single parameter A here for the energy here, and one H chi for this contribution here. If you take the derivative, you get the stress. You get generalized Hooke's law, where you have the double stresses proportional to K here, in fact, with this material parameter. Okay, this is the first assumption, a simple case. And now look at the Schmidt law, generalized Schmidt law. Remember, X was related to the relative stress, which is nothing but the curl of the double stress, but the double stress is proportional to the curl of micro deformation. So you have simply that X is the curl of the micro deformation. And this is how the second derivative of plastic micro deformation here come into play in the in the yield function that you have here. Okay, let's take an example. We take the usual, very simple example of confined plasticity in a periodic material. Simply you have a soft plastic phase with one single slip system. You have an elastic phase which does not let dislocation enter here. And this is a laminate under periodic boundary conditions. The classical solution is homogeneous strain in each phase, which does not look like the picture of HB, where you have some curvature of the lattice plane if the distance between the two elastic parts here is small enough. You can recover this by means of the micromorphic model that you have these pileups of dislocation at the boundary. We can solve analytically this problem. I will go inside very briefly to introduce what Stefan will explain. So simply we have one single slip system. We will have an applied glide here, gamma bar, and we will look for the vertical fluctuation in this periodic laminate, and we look also for this shear of the microplastic deformation. Okay, well, it's an exercise, easy one that you can do with students. In fact, it's nice that because you can compute the curl and then again the curl. Okay, let's drop this. Let's look simply at the solution. In fact, what is very important in the analysis are the interface conditions. What are the conditions at the interface between elastic and plastic domain? We assume continuity of the micro deformation. We assume continuity of the double traction vector, so the most simple rules we can apply, and of course continuity of displacement and traction vector, classical one, and periodicity. If you do that, you get this profile here. You get the profile here, you have the soft phase, the limit is here, and you see that you have some microplastic deformation in the plastic phase, and you must have a bit of microplastic deformation also in the elastic phase where there is no plastic slip, but to transmit the double traction you have to activate this mechanism close to the boundary. This is related to the internal length that you put in your material parameter here. Let's have a look at, here you have the plastic slip, look, you have the amount of slip, gamma. It is of course 0 in the elastic phase, but the micromorphic variable is not 0 in this part because you transmit the higher order tractions. Okay, the result is this. You get a very simple response. In blue, classical response without any gradient. I put no hardening here, and the gradient, the curl in fact here, yields to linear kinematic hardening. Look, you have it like that, which is dependent on the width, of course, of the channel in the model. Okay, then you can go to the limit, where you enforce the constraint that the microplastic deformation is equal to the plastic deformation. Then you get strain gradient plasticity. And you get this result, which is interesting. You get that you have a critical reserve shear stress, the classical value, and you have additional hardening. This is the mean shear stress. There is linear hardening, as seen on the curve before, but this modulus depend on the higher order parameter, on the volume fraction of the soft phase, but also on the size of the unit cell. And you see, it's related to the inverse of the square of the unit cell. And when we found that, we looked into metallurgy handbooks, and we found rules where you have a dependence in 1/L, and we found rules where you have a dependence in 1/the square root of L, but we found no example in physics, in physical metallurgy, where you have a dependence of 1/L square. And so it means it looks like reality, but the scaling is not the proper one, so we have something to abandon in the theory. And what we proposed was to abandon the quadratic potential we are assuming in the theory, and this is what Stefan will explain. And you will see in Stefan's presentation, I will skip this, in his last picture will be this one, because he will compute all this. He has tried two potentials, a rank 1 potential, a logarithmic potential. So let's look at simply the red one, and you see the loop is completely different. You start from here, you have a higher yield stress here, then no hardening, then you unload, you have kinematic hardening, and suddenly you have a jump here, and you have a non-convex plastic loop. So things that are very strange. It's a bit more beautiful with logarithm because you have some hardening also. So we thought, what is it? Strange. But in reality, it exists. If you look at the paper of Azaro, in a very old paper, he gives some example of experiments on a superalloy, in fact, where you have indeed some strange shape, at least for the first cycle. And after that, if you accumulate, you will see that you get the classical one. Look, the classical cyclic loops are like this one. But in reality, you may have such strange loops that can happen in some materials. Okay, so I will not insist on the examples, but since I have seen that, I see them everywhere in many loops, in fact. So we have many examples in the 70s, in the 80s, and also in the years 2000. You have examples in aluminum alloys of these things. And we had a discussion 2 weeks ago with Marc Fivel working in Grenoble, and we looked at this and he said, I am sure I can produce this with my dislocation. I am pleased to show his simulation here, because with almost nothing, just a front grid source that Claude has introduced earlier, so it's easy for me now. You have two pinning points here. You have a loop, the dislocation arm which bends and curves, and then the stress increases in shear, and once it's high enough, you have the Frank-Gehry source which start working, then it produces loops, and the stress is constant, then you unload. And when you unload, don't look at this, this is simply because there are not enough points here, it's sharp in fact. And when you unload, the loop will constrain again. They don't change the slip plane, so no cross slip. And then you will destroy again the remaining loops, and you still have this source here. And then you shear in the opposite direction, so you will form a new loop in the opposite direction with a jump again, like that. So this strange shape, in fact, can be interpreted also as a mechanism for a single loop, a single Frank grid source. In reality, of course, you have to add the cross slip and many mechanisms, and you don't see it in most cases, in fact. To operate, you must have, for instance, precipitates, where the size of the source is dictated by the distance between precipitates, and all the alloys I have shown here are reinforced with small precipitates. In fact, I thank you.
What's your opinion about adding to the model also dissipative higher order effects?
Okay. In principle, we should also consider dissipative processes. I think this is surely interesting, but in that case, in this simple case, I don't need it, in fact. So perhaps from viscous effect, perhaps we should need some dissipation also.
They give freedom to develop some positive equations.
Yeah, perhaps.
They have also I don't like that for the mechanics.
It's possible, but for instance, these strange loops, because they exist sometimes, but usually they don't exist. So probably we have to add this dissipative effect, which destroy this perfect order we have in the purely hyperelastic case. In fact, probably, but I don't know which kind of constitutive equation then.
Thank you.